Hi. So let's get started. So before we start, any question? If no, then let me we briefly talk about, say, just first is Amin. Oh, I haven't shared the screen yet. So just to remind you, the deadline of the first homework will be 24th. So this Sunday. Okay. So make sure that you submit your homework on time. Second thing is about sampling. Okay. Sampling distribution. Okay. So and I want to review a little bit before we go for today's estimation. The reason I want to review it for you because we will be using the technique here, okay, for the purpose. Okay. So let's get started and see how this topic is about. And after the review, I will try to, because we're in the lab, I'll try to show you how to do sampling in R, and then and you will see how the theorem in the we discussed would be a useful thing. Okay, first would be the sampling distribution. Just a very brief review. What we're talking about is first is a simple random sample. We said if each element has the same probability being selected, and whether the value of the first element doesn't affect the second element, right? It's possible that the first and the second sample, first and second observation have the same from the same subject. That is all perfectly fine. And the meaning of this is means that each observation the same mu, same mean mu, which is the population one, same variance and zero covariance. Okay, and the first thing here is the sample mean. Okay, sample mean is the average of the observations, and this sample mean will tend to be the have a good property, which because each observation have same expectation as the population mean, so that's why the expectation of the sample mean is also same as the population mean. Okay, and but probably the question would be later we'll talk about. Today is if each observation by itself have the same property. Okay, why we have to use sample mean to estimate population mean, right? Why don't we just pick up one sample, one observation, then done, right? We don't need to calculate the sample mean, right? We just pick up any observation, it will have expectation as the population mean. Okay, we'll explain to you later today. That's related to a good property called efficiency. Using this, you are getting more accurate. Okay, indeed, you can see that from this example is the variance, okay, of this sample mean is sigma square over n, okay, which means that the variance gets smaller compared to a single individual observation. One observation, okay, the variance of that observation will be same as the population variance. But when you have the sample mean, okay, the variation gets smaller. Okay, so you got a better estimate, more accurate estimate. Suppose we want to estimate the population mean as we will do today. Okay, and sometimes the standard deviation of this guy is called the standard error. Okay, so that is the expression here. Okay, and so we have just said the sample mean has same expectation of population mean, and the standard deviation, right, will be the square root of this guy. Okay, we just shown. So what central limit theorem essentially said is when n go to infinity, when as the sample size become larger and larger, okay, this guy, okay, x bar minus mu, right? I mean, when the sample size get larger and larger, this one is very close to this one, right? But still, in reality, they're never the same, okay? So at the end, they have some distribution, right? So, and then you normalize it by the sigma over root n, it becomes a bell curve, okay? So this is a important result. And of course, this is a good approach. This is only hold for n go to infinity. So in practice, we never go to infinity. So what we're going to do is when n is more than 30 something, that is a good one. Okay, so that is what we call central limit theorem. And in the case of special case of binary data where x is 0 or 1, okay, the sample mean of that one we'll call sample proportion, right? Because if you call one success, 0 fail, right? And you calculate this, it's exactly proportion, right? Suppose you have data of x is 1 or 0, right? Maybe 1 is, you ask the question whether the subject likes mirror, right? Or error, or whatever they like, right? And this is 1, right? Those who don't like with 0, right? You calculate this over a total number of them is proportion, okay? So that's why this, in the special case where 0, 1, that we call the sample proportion, okay? And just an interesting thing that because of the 0, 1 and mean and the variance are given by the same parameter, right? Mean if the proportion, the population proportion is pi, the variance is pi times 1 minus pi. Okay, this is what we learned in the previous chapter, okay, in the random variable. Okay, so this is follow from what we said is expectation of the sample mean is the population counterpart. Okay, and so on with the same, but only different is now this guy become pi times 1 minus pi. Okay, it's not p. Okay, and the next part will be saying applying the central limit theorem. Okay, that this guy, okay, will be approximately normal. Okay, so and that actually means one of the following is if I just last time I just skipped this part, but some of you asked me, so I just quickly go over it again. So what does that mean? It means that by this central limit theorem, binomial can be approximated by normal. Okay, what do I mean by that? Is if x follow a distribution np and n minus p, okay, at least 5, okay, that means, okay, we will say x is a binomial with n and p, but now we can say x just follow a normal. Okay, and how do we prove that? It's just basically coming from this below, you multiply n by the both sides. Okay, you multiply n by both sides. But anyway, this is the proof, but we're not going to prove. But the application would be if you know x is binomial with this, we're going to calculate this, okay? Because you use we call this can be a normal, okay? Because x is binomial with np, okay? But now, basically it's like this. If x, okay, can be a binomial with this n and this p, and you check np is bigger than 5, okay, then it's binomial, but now you can consider it as a normal, okay, and then you can use the same concept here to do the job, okay. But of course you can actually track this, okay, by using the Excel, right? Because this is what? This is just binomial. This 5400 0.6 true. Okay, so let's show you in the Excel. I think Excel here. Okay, so you can see this answer slightly different, but there's some adjustment you can do to make it work. But you can actually see that this number will be related to this one. Okay, of course, to get a much better estimate, you need to make some adjustment. But it shows that this is a good approximate. Is a reasonable approximation. Okay, and lastly, we talk about this guy. Okay, this guy is also looks very important. We will talk about this today again. So this is similar to this one, right? The only difference is this guy is we know the sigma. Okay, we know how the variance of the population. Okay, but the fact that in the real world we never know sigma. So what we do is replace it by the sample variance. Okay, and by doing so, we want to know what is this result of this guy. Okay, and later we will explain why we care about this. At the end of today's class, you should know why we care about this quantity. But this quantity, as someone showed it in 100 years ago, this follows student T. Okay, and you may ask for student T. Just remember student T, just a bell shape. It's really a bell shape, but has a bigger tail. Okay, feather tail. So it's a bell shape. It's symmetric, but have a larger kurtosis. Okay, or you can imagine a bell curve. You stem at the top, raise the two sides a little bit back, little bit off. Okay, so that is. I hope this is a good. It's enough sufficient review for what we have done. Okay, so now I want to go to our studio to show you why why these are true. Okay, why this formula is true. Okay, so what we're doing is go to our studio. I hope you open your our studio. Okay, and go to your package. Okay, and we will install the following package called G2s. So we will do two things. First, we'll calculate the hypothetical sample mean. Okay, mean of the sample mean, and then also we will be doing a simulation. Okay, the two things we are doing for the R for the moment. Okay, so let's install the G2s. Okay, so we install G2s. So once you're done your library G2, so that is the first thing to do. G2s. Okay, so this is the first thing we're gonna do. So I hope everyone have installed that. Is that okay? So I want to show you how to what would be the sampling looks like by showing you the some calculations. Is that okay? Everyone, is there any problem? Let me know. Okay. If that's okay, then actually we will be referring to this particular slide, calculate mean of the sample mean. Okay. So what we'll be doing, let me explain this slide before we go to this first. So we're using G2s. Okay. This G2 is a very useful group of the tools that is useful for our purpose. So what we're doing is called G2's permutation. Okay. This G2 permutation, what it's doing is you tell them that you're going to have 3 objects. Okay. 1, 2, 3 objects. You pick up 2 of them. Okay. And then you just do all the combination of them. It's a random sample. So repeated allow means that actually you're doing, this is actually asking them to do, you give them 3 objects, okay? And out of the 3 objects, you're going to do a simple random sample, okay? And that will collect all the random sample into this stuff, okay? And then the next step is I want to calculate what happened. Oh, I see. So the thing is, the second step is I want to calculate the sample I generate. I want to calculate sample mean. Okay. So I generate all the sample, is possible, different combination. I want to calculate all the sample mean. Okay. And once I've the sample mean, okay, of each sample I've drawn, okay, I calculate mean of those sample mean. Okay. So this is expectation of sample mean. Then I will show this will be same as the overall thing I do. Okay. So let me show you the math here. Okay. If you don't want to do it, you can just copy here. Doesn't really here you can see there's a bracket here, which means that I show I want to, after I run this, I want to show this result. Okay. So you don't have to have the bracket. The outside bracket is not necessary. So I just don't copy the bracket. I just do this one. Okay. So what it's doing here is, let me clean this up first. Okay. Okay. So what it's doing here, you can see, okay, look at this one. They're trying to tell you, okay, different combination, right? The first one is 1, 1, okay? And there's a 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Okay. So so there's actually missing optional statement. Okay. Here they have is 1 up to 3 here. Okay. So which means that when I don't specify, it will tell you just basically 1 up to 3 means that you're picking 3 numbers, 1, 2, 3. Okay. There's 3 numbers there. The software is trying to say 1, 2, 3, and you pick up 2 numbers there. Okay. All combination of 1, 2, 3. Okay. So basically what this is doing is the following. So you have, now we have 2 x1, x2. Okay. Now we have 1, 2, 3 here, 1, 2, 3 here. So that will be 9 different combinations. Okay. So what it's doing is the random top sample actually give you all 9 combinations. Okay. Is that okay for this one? Okay. Then what we want to do, okay, is to have a because I want each row, I want to calculate the mean. Okay. So there's a quick shortcut to that called row mean. Okay. So I call sample means. This is something like this that I do. Yes, sample means. Okay. Is equal to row means. Okay. For a random sample. Okay. So what it do? small letter there. Okay. So what you're going to do in this one is, let me display this guy again. Okay. So what it's doing is for each row, you calculate the mean. Okay. So this 1, 1, the mean is 1. 1, 2, the mean is 1.5. The next entry is 1 and 3, the mean is 2. Okay. So basically it's the mean of each random draw. Okay. So maybe I display this again to let you have a better idea what's going on here. Okay. So you have all the random sample, 1, 1, 1, 2, 1, 3, 2, 1, up all the rest, and basically calculate mean for each one. Okay. This is the mean of the sample mean, right? So we can calculate the following: mean of the sample mean, right? The sample means. This is the expectation, okay? So we expect this guy should be same as, would be equal to 2 because 1, 2, 3, right? So that's how you calculate 2, okay? So this is same as this guy, okay? So you can have fun in this way. Now, instead of 1, 2, 3, right? What you're going to do is you just write down anything you like, maybe 5, 4, 6, 10, okay? The 3 number there, okay? And then you draw 2 number there, okay? And see what you get, okay? So if you do this, okay? Let's display this, okay? There will be 9 possibility, right? 4, 4, 4, 6, 4, 10, 6, 4, 6, 6, 6, 10, or 6 possibility, okay? Then you can go on, and for each possibility, you calculate sample mean, right? That means that the mean will be calculated by this, okay? This is sample. This is the, for each sample, possible sample, you have the mean, right? And at the end, the mean of the sample mean is 6.666, okay? We want to verify, is it true? We calculate the mean of this, right? Mean of this 4, 6, 10, which is our original sample, okay? Which is the same, okay? So that verify the first thing, the mean of the sample mean is the population mean, okay? Of course, you can take more fun, right? By having n is a bigger number, right? N may be like, you can make n is like 4, okay? You can make 10 become 12, okay? And you can see at the end, you should get the same result. Let's run this, okay? You will see I have the same result. Both the mean of the sample mean and the population mean are the same thing. Okay, this is the first one I want to show. Okay, and here I just have a sample of 2, right? Indeed, you can make it more fun, make a sample of 3. Okay, there's no, okay, although it's getting increasingly crazy, but this is the same result. Okay, so no matter how you change the number, change your fun, get the same result. Is that okay for the first one? So this is demonstrate the idea why the mean of the sample mean is the population mean. Is that okay? Any question? No? Now the second step is to show the variance of the sample mean is 1 over n of the population variance. Right? So that is one to show. So how do we show it? It's not difficult. But the problem would be the variance of the we have to be a little bit careful because the variance in Excel is n over is over 1 over n minus 1. Okay, it's a sample variance, so we have to be a little bit more careful when we calculate that. But doesn't matter. Okay, so we need to have to be more careful. So this variance, remember in the Excel has to be is a over n minus 1. Okay, so we need to be a little bit more careful when we calculate this one. So one way to do it is to pick up our O function. I think we define it. So let's go back to chapter 1. Let me grab the function over there because we want the population version. So I think we have the function there with this one. Okay, I just copy this guy, variance dot p. Okay, we need to use this function. Okay, and what we're going to do is to show you. Okay, this, if you still recall, this is the population variance. Okay, this is a variance function. I want to use this function. Okay, and I want to apply this to calculate the variance of all potential sample mean. Okay, it's 3.33. Okay, then what I want to do again is to show you that this variance dot p of the population one is 10. Okay, yes. Okay, this is 3. The reason why is this is sigma. Okay, this is sigma t sigma square. This sigma square over n. So when we number of the sample is 3, so this is 10 over 3. Okay, so let me repeat. I'm not sure you're following. Okay, so here this is function of the variance. Okay, remember what is the sample? Let me do the sorry. Let me do the 2 sample. Maybe a little bit less trick here. So let's see this. Okay, so this is the sample of the. This is sample when you have 4 numbers. Okay, there will be actually 16 combinations of 16 possible numbers. Each one is equally likely. Now you can show it the sample mean is the same. Okay, AA. Okay, and then we calculate the variance. Okay, there's many sample. You can calculate variance for each. The sample mean is like this, right? You can calculate the variance of this. Right, and this comes from the variance dot p sample mean, which is 5. So this, all this sample mean, okay, possible sample mean, the variance of this is 5. Is that okay? And what we want to show is this, how this relates to the population one. Okay, the population one is 10. Okay, and why it is half? Because you do 2 sample. All right, if you do 2 sample, the variance sample mean is divided by half, sigma square over n. Okay, remember the formula. What I'm showing is this formula. If you are still confused, I'm showing you this formula. This is 10 here. You have 2 sample. This is 5. Okay, so this is trying to show you these 2 formula are correct. okay, by using R, okay. Ask the program to do whatever sample to do all possible sample, right? And this is what expectation means. Is that okay? Any question? The next thing I want to show you is a little bit more fun, okay? Of course, what we have been covering is technical. So if you don't fully follow, it's fine. You can just run it by yourself, okay? So modify the code to calculate the population variance and to calculate this. Actually, we have done it, okay? Then if you want to do it, okay? Okay, maybe I let you to try to work on this one. Okay, modify the code, okay? So that it will be maybe that's fine, just don't bother. Okay, I want to show you the next thing, okay? It's this one, okay? This one is asking you to actually let the computer to simulate data drawing, okay? Before that one, before we have this one, it's just hypothetically calculate all possibility, okay? It's not something real, you may say, okay? But what we are doing now is actually we are asking the computer to draw this, okay? So what function we'll be doing is they call the sample, okay? This is the function. What is asking here is ask the data, the computer, okay? From the data vector 1, 2, 3, 1, 2, 3 is 1, 2, 3, right? I draw two numbers, okay? And I replace because this is sampling simple random sample, okay? So let me do this in your, I show it here now first, okay? What it's doing here, let's do it here. Sample 1 up to 3, I draw 2, and I have replace is equal to true, okay? So what we'll do is, this is a vector, okay? You draw two number, okay? So what you're doing is, if I run this time, actually the data draw is 3 and 2, okay? Each time the draw is different. It can be 3, 1, and number is possible, okay? So this is asking, repeat again, is I have number 1, 2, 3, okay? What it's doing is, I ask the computer to draw one number here and draw again, okay? And I say replace true, which means that once I draw, I still have the same set of numbers, okay? So this is sample actually means simple random sample, okay? And 1:3 means I have a vector C1, 2, 3, okay? So if you don't like this 1, 2, 3, you can put what you like there. Okay, so example, you can say C 4, 6, 10, okay? 3, 4, 10, okay? So then the computer will just try to pick up any two elements. This is a simple random sample, okay? So now what I want, okay, is to draw 1,000 of this sample, okay? So what is the code for this one? This will be given by what we call replicate, okay? But the first thing we just want to we don't want to save so many stuff, okay? So what we want is once we draw the sample, calculate mean, okay? So this means we draw a sample and calculate sample mean, okay? This line. So instead of just draw the sample, we just go one more step, mean of this, okay? This is calculated. This line means I have a random sample of 3 number, 3, 4, 6. I draw two numbers, okay? And I calculate sample mean, okay? This need not be 2, okay? Can be a big number, doesn't really matter, okay? Okay. Just to remind you, this need not be 2, it can be 5, doesn't really matter, okay? Because when you say 5, then we just draw 3 fit those numbers. Okay, so this is the sample size. Okay, so maybe you can say, you can make your life easier, n is equal to 5, and make this n. Okay, and to make our life easier, we can say population is this guy. Then later we can change our code with our complication. Okay, so this is our code. Okay, and now we don't run this code anymore because we just want to calculate sample mean. Okay, so basically what we're doing is, I have a population is just 3 numbers, you can pick up whatever you want. What I'm trying to do now is a sample means that I draw randomly 5 numbers there. Okay, and I calculate sample mean. Okay, and that actually, this thing is the randomly generated sample mean. Okay, just random pick of 5 numbers going to mean. Okay, so what we want to do is to do this thousands of times. Okay, so what is the code there? It's called the replicate. Replicate. Let me don't do 100 times first. I just do 10 times because I don't want to my screen exposed. Okay, let's just copy this line. Okay, what here means is that I repeat this random sampling 10 times. Okay, that means I draw a sample of 5 10 times. So which means that I have 10 sample mean. Okay, so once I do it, actually you can see I have 10 very quickly. I have 10 different sample mean. Okay, and of course I can make it more crazy. I can have 100. Okay, that will be very quick also. Okay, it's very fast. You have 10 different sample mean. Okay, and each sample is sample of size 5. Okay, because n is 5. Of course, you can change n by any number. Okay, and what we want to do is to the 2 things you can do here. Okay, one is to first thing is to say I save it to my data. Okay, this is the sample. Maybe I go data. Okay, this is data. Okay, this is a set of the sample mean. Okay, oh sorry, I forgot there. Okay, the data look like this. Okay, it's a bunch of sample mean. So the first thing I want to do is I want to calculate the mean of the data. Okay, this is what is it? It is the different sample mean. Okay, I want to calculate mean of this sample mean. Okay, so this is 6.002. Okay, so this is not too far away from the actual population mean, right? Because the actual population mean of population, okay, this population mean is 5.6. Okay, so a little bit far away, but let us do a 1000 replicate. Okay, so the 2 should be very similar. So let's do 1000 replicate. Now it's much closer to this one. Okay, and now maybe we don't want to do more than 1000, would be 10,000. Okay, it's very close, you can see. Okay, so this is first thing to show you. Okay, is if you really do a lot of sampling, okay, using a computer, okay, that when this is actually fit our intuition, right? Okay, and second thing we want to show you is the central limit theorem. Okay, we said the sample mean, okay, would follow a normal distribution. Okay, we try to show this from the data. Okay, and we will see when we have a larger sample, we will see how it converges. It will look like more like bell shape. Okay, so the first thing here is this is data. We use the ggplot to do the plotting. Okay, so what we're doing will be following this. We'll do the plot. Okay, we do histogram, I guess. So what we do is we need to install ggplot. If you haven't, just ggplot2. I think it's there already. If not, just go back to the top. We have the library. ggplot2. Okay, library ggplot2 here. Okay, so we want to plot how this looks like. ggplot2, and what we need is to data. Okay, and let's follow what you have here. We use oh. So first thing is I had to convert it to data.frame first, because otherwise it would not recognize. Okay, maybe I call x is equal to data. Okay, let's do this. Okay, x is data. So I would just do the x is x, and I'll do histogram, I guess. So go to histogram. Okay, histogram. I just try to follow. Maybe, yeah, it's fine. Maybe I just plot this. So you can see the graph here. Okay, what I plot doesn't look really much like a bell curve, right? Because here n is very small. Remember, when n is 5, it doesn't apply central limit theorem, right? You have to have 30 something. Okay, so let's increase the sample size from 5 up to 10. Say increase 10 first. Okay, and let's run it again. Okay, is it getting more? Looks like a better shape. Okay, and let's now get it to say up to 30. Okay, run it again. Okay, it looks like increasingly like the bell shape. Okay, now as we want to make it to 50. Okay, so you're getting very much like bell shape. I think we have to reduce this beam width to make it looks like better, maybe, or if we increase the population. Okay, doesn't really matter what we add there. Okay, and it's getting increasingly looks like better. Maybe we just reduce the beam width to make it look better. So we just increasing look good. Okay, and we just increase the n. Okay, that will give us even more like a bell shape. Okay, so this is central limit theorem action. So that's why the sample mean, okay, is giving you the nice shape. Okay, even though it's not bell yet, but this is increasingly like bell shape. So I hope I convinced you that the sample mean actually looks like a bell curve. So this is a central limit theorem. Okay, because the sample mean indeed is a bell shape. Okay, I think I should have a break. But in the meantime, I will answer any question you might have. So just to show you that this is the bell curve. Okay. So let's have a break of until 9:30. Okay. So we just showing you how the central limit theorem applies and why the sampling distribution looks like what we have just said. Some of you said understand but worry about replicating this. But as I said, this R is a technical part, so I'm not expecting you to replicate what I'm doing either in exam or what. But just to let you know, this is actually what we taught is actually has you can see, right? And simulation is just trying to show you some way that programming can be trying to replicate or try to looks like what in the real world what it is. Okay, so it's not an intention to let you learn at this stage, because as I told this other people, and then that to learn simulation is already itself a whole class, the whole course of in statistics. So that's why we're just scratching the surface of simulation, and that's it. Okay. And what we want to do the rest of the class is to talk about estimation. Okay. And we'll probably not be doing the R or Excel, so don't worry. I mean, this the rest half of the class will be doing is some math. Okay. And the math here will be what we'll be doing. The math here will be conceptually difficult, but it's not any calculation. So you should understand the logic. Okay, logic is a little bit more convoluted. Okay, but I try to make it as simple as it can be. But if you can't follow, let me know. I just try to convince you this is right. Okay, so first thing, just some definition. Okay, but it's nothing new, but just nothing very difficult, but just a terminology. Okay, first we have population parameter. Okay, parameter means the things that usually we're interested in, like mean, variance, mode, kurtosis, IQR, all those kind of thing. And it's called parameter. The reason is because there's not random variable. Okay, this is something that exists, but we don't know, right? Just like the income of everyone in Hong Kong, right? And the income of the people or family of individual, their number that is there, but is no random. But the problem that why we have randomness is because we have to use sample to figure them out. Okay, because if we know it, we ask everyone's income, okay, then we know the average income. But sometimes we can't, right? Income you can ask, right? But if we want to know how many students in CHK like, say, Mira, right? Then it's not something we know, right? Then you have to ask everyone whether you like this or that, right? So the thing is, you from the data, okay, to get the parameter we want is called estimator. Okay, one example is called sample mean. Sample mean is an estimator, right? Because I give the data, okay, you can calculate the average of them, okay, and that sample mean is used to estimate the population mean. Okay, so that is called estimator. And once you have the data, you calculate the actual sample mean. It's called estimate. It's the realized value of estimator. And we'll focus on two different estimator today. Okay, first one is called point estimator. We just give a number. Okay, like sample mean, sample variance. Okay, these are called point estimator. Okay, we also know sample kurtosis, sample skewness. They are all example of point estimate because they give a number, a single number. Okay, and after that, this is nothing deep, but we'll go to talk about interval estimator, which means that instead of giving a single number, we'll give a range. Okay, and a typical example would be people, you look at the financial news and you ask the expert and say, oh, what is expectation of today's stock market, Hang Seng Index, right? And if the guy said today's Hang Seng Index will be 25,000, okay, that's a point estimate. Okay, and if the guy said today's Hansen index will be between 24,000 to 26,000. Okay, that is an interval estimator, right? Because it just gives a range, and you are claiming that at the end it will be somewhere there. Okay, because you're asking the guy to estimate what's going on at the end of the day, right? So that is interval estimator. Okay. So point estimator, okay, and we will start by giving you two property, okay, actually three, but the last one is technical. Two good property that you would want to say which point estimator is good or bad, okay. The first one is something I think is rather basic, is we want, okay, the expectation of the estimator equal to one estimate. Okay, it means what we have is expectation of the sample mean is the population mean, if you have about mean. Okay, and actually we have shown in the last class, right? Expectation of the sample mean is actually the population mean. Okay, there's nothing surprising there. Okay, and what about sample variance? Okay, the sample variance actually satisfies these two. The expectation of sample variance is actually population variance. Okay, and as we will try to show it later, a few slides afterward, we will try to give the proof why we need to divide by n minus 1 instead of n. Okay, n minus, if you divide by n minus 1, okay, it satisfies the unbiasedness. If you divide by n, you'll be biased. Okay, so hypothetically it means the following. I mean, graphically, it means this. Okay, it means, suppose, I don't know whether you play the game holding a dead or archery, right? You're trying to hit the blue eyes here. Okay, I'm not sure whether. Okay, archery, right? So you try to have an arrow, right? So we'll try to shoot the arrow to go. Okay, this is the population parameter, right? You want to hit this guy. Okay, so what unbiasedness means? Unbiased means graphically means the following: every single attempt need not be hitting the bullseye. Okay, but on average, say this case, on average, the middle point is hitting it. Okay, so that means this guy is an unbiased archer. Okay, he's not hitting it, but on average of this hitting it. Okay, whether this is good or not, but this is the basic one. Okay, and this is the first called unbiasedness. Okay, and the second one is called efficiency. Okay, which says if we consider two archers, okay, that are all unbiased. Okay, either this guy, the green guy. Okay, maybe this is a green guy. Okay, this is it's a green guy. Okay, and I have another guy called okay. Okay, so you like the green guy or like the orange guy? You would prefer to be green guy, right? Because the green guy is closer than the orange guy. Okay, on average, they're hitting the thing. So that's why from A and B, A, the variance smaller than B, then it's more accurate. Okay. Now, we try to justify why we use sample mean. Okay, the first thing to do. Okay, we're not going to do the proof, but I just give you the idea to get the proof. Okay, so that will be the next. That will be the thing in the just jump a little bit. So just the slide number 7. Okay. So why we are using this? Okay, a sample mean. Okay, and the proof goes following. I'm not going to go to every single step, but just say, suppose I use a weighted average. Okay, and a weighted average. Okay, you can solve. I'm not going to do it because we need Cauchy-Schwarz inequality. If you know math, then it's not difficult. But what it shows is the mean of any weighted average is bigger than simple average. Okay, so that's the reason why we are using simple average, because it has nice property. Okay, and you can easily see if you use any, you drop any observation, okay, any observation you drop, we will have a bigger variance. Okay, so that's why you have to use up all the information, okay, over n. Okay, so that is the first thing to say, why we use sample mean all the time. Okay, that's why we don't use geometric mean, we don't use harmonic mean, we don't use other mean, right? Because either they are unbiased, they are biased, or they are not efficient. Okay, and besides unbiasedness and efficiency, there's another one. Okay, it's rather technical. It means the following. Okay, it means what it said is, if you increase the sample size enough, okay, it eventually hit the target. Okay, I may repeat, it means the sample mean, the difference between sample mean and the population mean will be as small as you want. Okay, bigger than any number will be equal to 0. So the probability that the distance is further than any number you say will be 0. Basically, just like they will be close to each other as small as you want will be 1. Okay, the complement means they will be, if n get bigger and bigger, the sample mean will be approaching the population mean as close as you want. Okay, if you want bigger n, it will be closer and closer and closer. Okay, so that will be the probability, because this is a probability statement, right? Because this, you cannot know it before you realize, so you have to use probability. Okay, so that is why I have a limit and probability, but we're not going to forget about this statement, but just saying that the difference of the estimate and the parameter will be as close as you want. Okay, and this, why I want to mention this, because this is a very useful property when you study more advanced class. Okay, because consistency is much weaker than unbiasedness. So at the minimum, you would at least want a consistent estimator. Okay, that's a basic requirement. On the top of that, you will probably want unbiasedness and efficiency. But this is more fundamental, right? Because this require you n go to infinity. Okay, and in this case, okay, you require any n. Okay, and if you unbiased and your variance is decreasing in n, which is usually the case, right? Because n is more, we have more n or more accurate, right? So usually unbiased usually imply consistency, right? Because usually you have more sample, your estimate will be more accurate. So that's why unbiasedness usually imply consistency. But consistency it doesn't equal to unbiasedness, but this is usually the basic requirement. But anyway, I'm not going to go to detail here, but you will see this if you do more advanced classes. Okay, so I basically convinced you that this is a good estimator because unbiasedness. Okay, and you can actually, we know this also consistent, and then we also show that this is also efficient. Okay, compared to other measure we are comparing. Now, I want to also convince you this is also a good estimator. Why M-1? Because M-1 is unbiased. Okay, of course, this is also, you can also show this a consistent estimator. But anyway, I'm not going to do the proof because we said we are not doing any proof in the class. So we just go to show the ideal proof is trying to show you this, okay? Going through all the many steps of calculation, 1 page of calculation, 2 pages of calculation, 3 pages of calculation. We indeed show this one. Okay, as I said, I promise you I'm not going to do any proof. Okay, if you want to do it, you can read it by yourself. If you're still confused, I can answer your question or ask the TA. Okay, I'm not going to the detail because I mean you will forget anyway. Okay, but I will just just repeat what is it is the expectation of the sample variance is this guy. Okay, so actually you can verify that by yourself. Okay, you can use R. Okay, if you don't want to do the proof, you can actually use R. Now with the technique, you can generate a sample. You can calculate sample variance. You can do it, right? Say for example, the following. Maybe I can just show it here. Okay. So I can, instead of calculating the sample mean, right? I just do it here. I calculate the variance. Okay. And note that this variance is the sample variance here. Okay. You can calculate the sample variance. I don't need this line this way. Okay. And I run this. Basically, I generate many sample variance. Okay. 10,000 sample variance. Okay. And what I want is to so the mean of this sample variance would be same as the population one. So mean of this simulation, okay, should be same as the variance dot p of this simulation of the population. Mean of this variance. Okay, so that's the same. So that's, I convince you that this is unbiased. Okay, what I'm doing is I just try to draw 100 sample. Okay, this is the population I have. You can, whatever number you do, and I just said from this population, okay, this data, I draw 1,000 numbers, and I calculate the sample variance. Okay, this VR in R, remember this sample variance. I calculate 10,000 sample variance. Okay, calculate the mean. Okay, I want this mean same as the population mean because we need to use dot p because it's definition. Okay, so you can see they're very similar. Okay, so this is unbiasedness. Okay, so you can imagine that if you use the instead of n-1 use n, then you will not be same. Okay, so I don't do the proof, but at least I demonstrate that it can be true. Okay, but of course, if you want to go to the proof, is that okay? For this one, any question? So just to try and show you that, I mean, even though you don't want to do the proof, this is something good. And just want to let you know that because statistics, indeed, there are a lot of things you can't really prove it, but that's why a lot of time you rely on calculator to tell the people how things looks like in different scenario. Okay, this is something, even though in advanced research, computer is also very useful because something you cannot see this visually. Is that okay? Is that okay? Any question? If no, then let me go back to the slide. Okay, I hope I convinced you this is true. Okay, but if you don't, you are not convinced by the R, just go through the math. Or 3 pages is not a lot. If you are able to undo the math, then it's not. Then you should be able to convince this is true. Okay. Now, in the same spirit, sample proportion is an unbiased estimator for the population proportion. Okay, because sample mean is a good thing for population mean. Sample proportion is good for population proportion, the same thing. Because just sample proportion is just the data becomes 0 and 1, just binary data. Okay, it holds for general. I just restrict to 0 and 1, the same thing. Is that okay for this one? So the question would be, okay, just application, maybe you are not really convinced or not sure what I'm saying is, suppose you want to know how many CHK students like Mira, okay? Then what we're going to do with good estimator will be sample proportion. So what we're going to do is you randomly go to the subway station, the station, randomly ask people, count how many people who like Mira, calculate proportion. That is a good estimator. It's an unbiased estimator. Am I myself clear? Did I make myself clear? Is that okay? Okay, so the sample proportion is a good one. Now, so it is unbiased, okay? So the variance is EP is pi. So what about the variance? Okay, how to estimate this guy? Okay, since P is a good estimate for this, okay, it is tempting to say P times 1 minus P is a good one. Okay, so but indeed this is a typo. It's not unbiased. So this is a bias. This is a bias estimate, but we will be using this. Okay, although this is a bias, there are some other reason why we still use this one. One of the reason is because when you calculate proportion, what is unbiased would be this guy. Oh, don't ask what is unbiased. This is unbiased. If you want unbiased, this is unbiased. Okay, and this guy is biased. Okay, and the reason why you don't need to adjust of this is because when you do proportion data, usually n is usually not small, right? You're not going to ask 10 people and just done, right? Usually have a big n, maybe a few hundred or at least 100, right? Then this guy usually is not a big deal, right? You can see when n is big, this is nothing, right? So that's why you would not be bothered, and that's why you would okay to use P times 1 minus P. Okay, so that is what we're doing in the next set of slides. Okay, but just to just to erase this is just make sure this is an bias estimate, but we're using it anyway. Okay, because there is no harm to use this. It's not usually not a big deal. Okay, just for simplicity, make our life easier, just use this one. Okay, and this is next thing. Okay, so we know how to estimate the sample mean, sample. We'll actually other estimate population mean, population variance, population proportion, variance of population proportion. Okay, you know all 3 of them, but 4 of them. Okay, so now we're going to call this set of slides is called interval estimator. Okay, what we want to do is instead of giving a number, we give a set of number. Okay, instead of guessing one single number, we guess a group number. Okay, what it means is instead of saying what is average income of Hong Kong people, instead of saying it is going to be 20,000, okay, per month salary, we're going to say it's going to be between, say, 180,000. No, it's going to be it's going to be 18,000 to 22,000. Okay, instead of saying 20,000. Okay, I'm going to add and subtract 20,000. Okay, to our guess. What it means is we're going to, this is what we mean, right? This is a number line, right? From 0, right? Point estimator is trying to do the following. I pick up 1 point, okay? Say sample mean, right? And this is our guess. This is my guess. I pick up particular number. This is my guess, okay? Interval estimator is, instead of going to talk about a particular number here, we are trying to suit them in a range, okay? It's like point estimator is just a rifle or gun, just hit 1 point, okay? I'm using a missile or rocket launcher or a nuclear bomb to bomb the whole area. So instead of asking this, I bomb the whole area like this, okay? It's a weapon of mass destruction, okay? It just destroy the whole area, saying I'm guessing this, okay? And what we want is to have a symmetric interval. So we call this is M, okay? And it's called the margin. Okay. I cannot write it properly. This is margin, okay? And this margin M, okay? We want this margin to be independent of the data. It's non-random margin, okay? The margin is not depend on where is the sample mean, right? So because sample mean is a random variable, remember, okay? This would change a lot, okay? We want this to be same. Just remember the nuclear bomb, right? No matter where you bomb, right? The area factor will be same, okay? Whether you bomb city A, city B, right? The size of this, the area of destruction is the same thing, okay? So the same idea. We want a non-random interval, okay? Okay, to say this is my guess. Okay, so let's go to, this is very difficult concept, so let us go a little bit slowly, okay? The math is rather simple, okay? But the concept is very difficult. So I just slow down a little bit. I do it, I may repeat myself several times to make sure you understand. Okay, what's going on here? First, I want to estimate mu, right? We know from the previous few slide, X bar is a good estimate, okay? And the motivation for this is, if I have a small sample, okay, I got the sample mean, okay? Suppose I have asked 10 people, the FA salary is 20,000. Compared to another situation, I asked 1,000 people. I also get the salary of 20,000, okay? But can we get a better thing to say rather than just sample mean, right? If later you will see, if we talk about interval estimate, you will expect the second one, which is larger sample size, the interval will be smaller, okay? Because we are doing more sample, get the same result. We're expecting that our sample mean is actually more accurate, right? In some sense, right? If we should be closer to this real mean, because we do 10 sample, we just do this. We happen maybe to be close to the mean somehow, but we have a much larger sample, okay, and we still get the same thing. It should be much more accurate, okay? Accurate in the sense that we don't need to make a so big atomic bomb to bomb this area, right? Because if we have a small sample, we need a bigger bomb, okay, to make sure that we hit it, right? But if you have, we know it's more accurate, we don't need to bomb so big, okay? So how we do it is actually relying on what we call central limit theorem, okay? The central limit theorem can tell us how to make the bomb, okay? Now, this is a normal distribution, okay? So we want to do the following, okay? We want to say, okay, the X bar, okay, plus and minus M would include the mu. Okay, so let me draw a picture to tell you a little bit more detail here. Okay, so first thing is X bar by central limit theorem. Okay, actually we do it in the R class, right? So it'll be something like this. Okay, so remember this is a random number. Okay, so what we want is, okay, we actually sometimes depends on what the data will give you. Sometimes it's here, right? Sometimes will be there. Okay, what we want is, we ask the question is, suppose we're asking each time we have a non-random interval, which means that m, okay, the size m, we go right by m, go left by m. Okay, each time when we draw this, we go right by m, go left by m. Okay, we want, so if here this is included, right, and if here this is not included, if you're further away, that is not included. Okay, did I make myself clear? So if maybe make the m smaller. Okay, what I'm doing. So the green here. Okay. So in the two cases, I use the red color. Very annoying. So both this case, to the m is not including the mu, okay? But if in other case, maybe a green one. Okay. In this case, green is included in the mu, right? And the red and the purple doesn't, right? So we want to construct to vary the m, okay? To make sure that if you do sampling in this way, most of the time we include the mu. Okay, let me repeat the statement. You do sampling, right? The sample mean will be here, right? More likely in the green, right? Because look at this one, more very likely the green one. And we want to say for each sample realized, right? We can go forward by m, go back by m, right? And we want this to include mu. Okay, we want our construction include mu. Okay, and because the probability, right? So we want many of those scenarios we include the mu. So we want to figure out the m. Okay, what's the m such that a lot of time, or say most of the time, okay, we would include the mu. That is what confidence interval means. Okay, of course, you want it to cover it more times, more fraction of time, then the m is larger, right? Because mainly it's inside here, but this possible is there, right? So if you want more time, you include the mu, okay, then you have to match the m is bigger. Okay, so in the other word, the mathematics is like this, right? It's like just in the notes is say the following, right? You want the mu is between x bar plus m and x bar minus m. This guy is very small. So this guy is very big. We want the mu is between x bar plus m and x bar minus m. Okay, this is the left and right. Okay, include the mu. Okay, so you can rewrite this into other dimension, right? We want mu is actually the m distance between x bar, right? Actually it means that the distance between mu and x bar is less than m. This is exactly the same meaning, right? So this is exactly the same as the following. same as asking this question, is asking x bar minus mu is actually m negative m. Did I make myself clear this one? Asking how to do this math, you just move the m to the other side. You get this. So you move this m to this side, right? Give this inequality. Sorry, you move mu to this guy, you m to this side. This one, you move this to this, this to that to give the first one. Okay. And now one more step to do is to do the following. I divide both sides by sigma over root n. Okay. And you may ask why I do that. Because this guy is standard normal by central limit theorem. This guy is normal. Okay. So this guy actually is called Z, right? We know it. We know this guy is Z. Right? So is that okay up to here now? Now let me rewrite this in the next slide. Okay. Is that okay for up to here? Actually, everything is in the notes already, in the slide already, but just write down in another presentation format. So what we want is, let me do in the next slide. Okay. I hope that's okay. So just to repeat the statement, okay. Just repeat here is what I have is mu is x bar plus m and x bar minus m. What we write is this guy, x bar minus, sorry, we simplify to this one, minus m over sigma over root n equal to x bar minus mu m over, sorry. Okay, this is just a simple manipulation of inequality. Okay, this and this you can prove by yourself the same thing. Okay, the same statement. Okay, and if we want this guy, okay, to be like 1 minus alpha, which we'll define alpha later, which means the following. This is mu here. Okay, actually we want, this is mu plus m, mu minus m. Okay, this is x bar. Okay, we actually want this guy to be 1 minus alpha. Okay, alpha is a very small number. Usually alpha is 0.1, 0.5, or 0.05. Okay, so basically I want it to be, say, 90%, 95%, or 99%. Okay, I want 99% of time. Okay, the interval will include the mu, or 95 or 90 or 99 times. Okay, and from this expression we know that this guy is what? This is Z, right? So this guy is exactly Z alpha over 2. Why? The middle one is 1 minus alpha. Okay, the both side must be alpha over 2, right? Because symmetric. Okay, and this guy is negative Z alpha over 2. Okay, just to remind you, how to calculate C alpha over 2, right? This is just norm S inward 1 minus alpha over 2. Okay. This alpha over 2. And this guy is 1 minus alpha over 2, right? This is the norm inverse of this. Okay. And then what is M? M is equal to this. So M will be equal to this times this. Okay. So at the end, we have the final formula here, which is the following. Actually, if in the book, I think this is the last formula is important. So the final formula is M is equal to Z alpha over 2 sigma over root n. Okay. So this is the goal of today. Okay. So if you forget about what we have learned, it doesn't really matter. The goal is that this last equation we need. Okay. As I said, I'm not requiring you to know the proof, but I hopefully convince you that the principle behind it. Okay. But I guess it's not important here. But let me go over the proof again. Oh, sorry. Go over the proof again here. Okay. So what we want is we have x bar minus m and x bar plus m is to include the mu with good probability. Okay. Alpha is a very small number. Okay. So we want this. Okay. So we will show in the next slide. Actually, m is this guy, which we have just said. Okay. So we want mu will be between these two. We will show this is 1 minus alpha. Okay. So that is the interval estimator. Okay. So what it means is if I know sigma, okay, and if I calculate the sample, I have given a sample, I calculate sample mean, okay, and I know my sample size, okay, and sigma is given to you, okay, this is given to you now. If not given to you, we'll talk about that soon. You will use T, you use S and it change to T, okay. But now suppose I know sigma, and this will be depend on the alpha, okay. The smaller alpha, the Z alpha over 2 is bigger, right? So that is the interval. Okay. The proof is the following. Okay. We know that if Z is normal CO1, okay, so it will be like this, it's equal to 1 minus alpha. And we know that this C is equal to C alpha 2. Okay, this is the definition, right? This is a what it said is this guy, right? It's just saying you have Z, if normal, okay, and if the area is alpha, okay, this is called Z alpha, okay. So this is what we learned. Now we know by central limit theorem, this is the rule, which means that this is standard normal. So it's between C alpha over 2 and negative C alpha over 2 is 1 minus alpha. This is by definition. And basically you can rewrite the inequality. That's what we want. Okay. But I think I have convinced you this is a proof. But nevertheless, if you don't accept the proof, doesn't really matter. So this is the last slide I want to talk about today. Is you have data, you calculate your sample mean, okay? And this depends on how big your interval is, alpha over 2, and you have sigma over root n. And this is we call the margin, okay? And left go by ME right over ME. So this 2 of the ME is the width, okay? And the lower part, the minus, the left-hand side is called the lower confidence limit. The upper part is the upper confidence limit, okay? And just one final remark, okay? Here you can see I have called confidence, okay? It is very important, it's not probability, okay? The reason this is very technically, philosophically difficult because the reason is mu is a fixed number, okay? There's no probability once you collect data. Once you collect data, the data is fixed, the mu is also fixed. You cannot say anything for probability. You can think before you do the collect data, you calculate the confidence interval, that you have 95% probability that what you found will include the sample, the population mean. But once you find that, you have no probability. Okay. So what is the confidence here means if suppose we repeat this procedure hundreds of times, okay, many times, then 1 minus alpha of those will include the mean. Okay, it's not probability. Okay, just repeat one statement before n because very important. It is not saying that 1 minus alpha percentage, the mean will inside this one. No, because all of there's no uncertainty here. Okay, because once you found out the interval and all the data are fixed. Okay, there's no probability you can say. Okay, what is probability you can say is before we do the random experiment, when we do the sampling. Okay, if you do before you do it, you can say 95%. When you do it, you include the true mean. Okay, but once you figure out that, it's no longer say so. But what you have in the confidence means that if you repeat your process 100 times, 95 of times, you will include it. Okay, you don't know which one, but this is the confidence where it comes in. Okay, so I should stop. I will see you next week. Just remember you submit your homework on Sunday. We'll continue this next class. Remember, next class is in this room again. Next Monday is in this room again.